All right, here we go. Quick lesson on some basics of acid-base properties. So first off, you've probably heard of an acid before. Usually it's not a warm, fuzzy thing you think of with acid. So some are dangerous, but they're also found in all sorts of medicines and foods that we eat. So let's look a little bit more into acids. So first off, there are many definitions of acids. The simplest one is called the Arrhenius definition, and this basically just says an acid is any substance that will dissociate or break apart to form H plus ions. So a classic acid we deal with is hydrochloric. It breaks into H plus and Cl minus, so it's an Arrhenius acid. Sulfuric acid will also break apart. Notice I only had it break into one H plus here. It can break apart some more, but I'm just looking at the first one here, so that's an Arrhenius acid. And this is sort of what an Arrhenius acid looks like in solution, the H pluses and the Cl minuses. One thing you are going to see in this unit is H plus and H3O plus are sort of used interchangeably. And the reason for that is when an H plus ion is in solution, right away it pretty much attaches itself to a water molecule to make H3O plus. And so whatever the concentration of H plus is, it's effectively the same as H3O plus because there's just billions and billions more water molecules that having an H plus join a water molecule doesn't substantially change the amount of water in there. So for all practical purposes, consider these to be the same thing. All right, so acidity, you can have things that are very acidic or only partially acidic, and typically the way we measure that is with something called pH. And the lower the pH, the more acidic something is. Now, this is not a linear scale, it's a logarithmic scale, meaning that like the Richter scale is how we measure magnitude in earthquakes. So a 7 on the Richter scale is 10 times stronger than a 6, and an 8 is 10 times stronger than a 7. So same idea here. If I have a pH of 4 versus 3, 3 is 10 times more acidic than 4, and 2 is 10 times more acidic than 3, which means 2 is 100 times more acidic than 4. So every single unit increases the acidity by a factor of 10. So again, anywhere between 0 and 7 is acidic, and it can actually even go below 0 for really acidic things. And then above 7 is going to be basic, or alkaline is another term. All right, so some properties of acids. One, they're sour. So this is what gives citrus fruits, so their sour taste is typically citric acid and some others. So they taste sour. They conduct electricity. So if you were to stick a bulb in a solution of acid, it would conduct electricity, primarily because of the H plus ion. They're very corrosive. I think we all sort of know that. You don't want to spill them on yourselves. They can react with metals, sort of eat through metals as a result. That's why they're usually kept in glass. In some cases, certain types of plastic are also good to store them. They often look like water. So this is a solution of acid, but it looks just like water. There's an old joke, Johnny was a chemist's son, but Johnny is no more, because what he thought was H2O was H2SO4. I don't know why I put that in this video. It seems like a waste of time. Let's move on. Litmus paper, blue litmus paper, if you dip it in acid, will turn red. So there's lots of different indicators we're going to learn about that have to talk about acids. So anyway, that's acids. Let's look at a base, which is sort of the opposite side of an acid. So the Arrhenius definition is that they dissociate to make OH minus. So sodium hydroxide, also called Bly, will break apart into Na plus and OH minus. Magnesium hydroxide, milk of magnesia, it helps treat stomach acid, will break into Mg2 plus and OH minus. So these are both Arrhenius bases. Oftentimes, if you see an OH on the end of a formula, a lot of times it's a base, at least if it's with a metal. If it's not with a metal, it's not necessarily a base. We're going to see substances that have carbon and hydrogen with OH on the end, and they are not bases. So only if it breaks apart, basically if it's ionic and has OH on the end, it's probably a base. All right, so same thing, pH measures if it's acid or alkaline. So as you go up, you get more basic, and that's the pH scale. There's actually a pOH scale we're going to learn about later, which is basically the opposite of this. On the pOH scale, the lower you go, the more basic you are, and the higher you go, the more acidic you are. So we'll see that more in another video. Properties of bases, they're very slippery. So soap is a base. They're bitter. So the taste of soap, you know, watch this movie, it's not very good. So bases, they're slippery and bitter taste. They are also corrosive. So a lot of bases you don't want to get on your skin. Sometimes they're not as corrosive, like soap isn't corrosive per se, but if it gets in your eyes, it is, right? It stings. But there are other bases that will do just as much or if not more damage to you than acid will. And again, they often look like water. They conduct electricity because of the OH minus thing, and they turn litmus paper, red litmus paper, blue. And I'm not going to quiz you on this, but if you wanted to know blue for base, that's one way to kind of remember this. All right, so pure water then is neutral. And the reason for that is if you had a beaker of pure water, meaning nothing but H2O in there, which would be hard to get pure, they actually react with each other. A water molecule, one of these H pluses will go to another to make these two substances, H3O plus and OH minus. And in pure water, every H3O you make, you're going to make an equal amount of OH minus, so they're effectively balanced. So pure water is neutral as a result. This equilibrium, though, is always going on, whether it's pure water or not. So in neutral water, the K value for this reaction is 1 times 10 to negative 14, meaning in pure water, a very, very tiny amount actually does this, called autoionization. So you're not going to see much H3O or OH minus, and it actually comes out to 1 times 10 to the negative 7th molarity each. But what happens if you start pouring acid in the pure water? You are adding H3O plus. And we know from Le Chatelier's principle that if you add H3O plus, you're increasing this, it's going to shift left. And as it shifts left, it's going to consume some of this OH minus. So basically, when you add an acid, you are removing OH minus, you're lowering. So if they're equal to begin with, as you add acid, you drop the base, so to speak. And if you add base, you drop the amount of acid. And so this is sort of what it looks like. When something's neutral, there's equal amounts of H3O and OH. As it gets more acidic, the amount of H3O increases versus the OH. But it's never, you never like have no OH or no H3O plus. There's always some of each. And the formula is that they will always multiply out to this value 1 times 10 to the negative 14. So if you know 1, if you know the H3O concentration, you can always find the OH minus using this equation. And that's pretty much, I say basically a lot when I teach this unit, I realize. That's pretty much going to sum up the basic points of acids and bases. So until next time, I am Derek Genova. Have a delightful day.